In mathematics, the Lambert W function, also called the omega function or product logarithm, is a set of functions, namely the branches of the inverse relation of the function f, z, equals z, where z is the exponential function and z is any complex number. In other words, by substituting in the above equation, we get the defining equation for the W function. For any complex number z. Since the function e is not injective, the relation W is multi-valued. If we restrict attention to real value W, the complex variable z is then replaced by the real variable x, and the relation is defined only for x a per million 1/e, and is double-valued on. The additional constraint WA per million 1 defines a single-valued function WO, x. We have WO, 0, equals 0 and WO, a 1/e, equals a 1. Meanwhile, the lower branch has WA per mil currency a 1 and is denoted Y1, x. It decreases from Y1, a 1/e, equals a 1 to Y1, 0 equals AA. The Lambert W relation cannot be expressed in terms of elementary functions. It is useful in combinatorics, for instance in the enumeration of trees. It can be used to solve various equations involving exponentials and also occurs in the solution of delayed differential equations, such as y, t, equals ay, ta1. In biochemistry, and in particular enzyme kinetics, a closed-form solution for the time-course kinetics analysis of Michaelis-Menton kinetics is described in terms of the Lambert W function. Terminology. The Lambert W function is named after Johann Heinrich Lambert. The main branch WO is denoted by WP in the Digital Library of Mathematical Functions and the branch Y1 is denoted by WM there. The notation convention chosen here follows the canonical reference on the Lambert W function by Michaelis, Gonnet, Hare, Jeffrey and Knuth. History. Lambert first considered the related Lambert's transcendental equation in 1758, which led to a paper by Leonhard Euler in 1783 that discussed the special case of O. The Lambert W function was rediscovered every decade or so in specialized applications. In 1993, when it was reported that the Lambert W function provides an exact solution to the quantum mechanical double-well Dirac delta function model for equal charges a fundamental problem in physics Michaelis and developers of the Maple computer algebra system made a library search, and found that this function was ubiquitous in nature. Calculus equals derivative equals, by implicit differentiation, one can show that all branches of W satisfy the differential equation. W is not differentiable for z equals a 1/e. As a consequence, we get the following formula for the derivative of W. Using the identity, we get the following equivalent formula which holds for all. Equals antiderivative equals, the function W, x, and many expressions involving W, x, can be integrated using the substitution W equals W, x, that is x equals WU. The form on the right is more common in the literature but does not hold at. One consequence of which is the identity. Asymptotic expansions, the Taylor series of around 0 can be found using the Lagrange inversion theorem and is given by the radius of convergence is 1/e, as may be seen by the ratio test. The function defined by this series can be extended to a holomorphic function defined on all complex numbers with a branch cut along the interval, a 1/e. This holomorphic function defines the principal branch of the Lambert W function. For large values of x, WO is asymptotic to where, and is a non-negative Stirling number of the first kind, keeping only the first two terms of the expansion. The other real branch, defined in the interval, a 1/e, 0, has an approximation of the same form as x approaches 0. Within this case and in it is shown that the following bound holds for equals integer and complex powers equals, integer powers of also admit simple Taylor series expansions at. More generally, for the Lagrange inversion formula gives, which is, in general, a Laurent series of order R. Equivalently, the latter can be written in the form of a Taylor expansion of powers of, which holds for any and. Identities. A few identities follow from definition. Note that, since f, x, equals x is not injective, not always w, f, x equals x. For fixed x,